You know, for centuries, certain math problems have been kind of filed away in a drawer labeled impossible. Not because we couldn't get an answer, but because getting a perfect, exact one seemed, well, out of reach. Today, we're going to look at a new theorem that says, hold on a second, and claims it can solve one of these impossible problems by showing us a hidden simplicity we never saw before. Let's dive right in.
So here it is, an eighth-degree polynomial equation. I mean, just look at it. It's complicated, it's got a ton of terms, and it looks like an absolute monster to solve. For a very, very long time, finding its exact roots, the precise values of x that make the whole thing equal 0, was thought to be beyond what classical algebra could even do. So why? Why was this so hard? Well, a big reason is something called the Abel-Ruffini theorem. It basically says that once you get to polynomials of the fifth degree or higher, there's just no general one-size-fits-all formula to solve them using simple stuff like taking roots. I mean, there's no magic formula like the quadratic equation we all had to memorize in school. So mathematicians had to get creative. And that creativity really led down two main paths. You could either get a good enough answer using approximation, or you could hold out hope for some kind of breakthrough that finds an exact one. Let's break down what that really means. Okay, so on one hand, you've got the classical methods. These give us approximations. They're super useful for things like engineering and physics, but there's always that tiny risk of rounding errors. Plus, they're fundamentally fenced in by those big theorems we just mentioned. But this new approach, it proposes something totally different, building an exact symbolic solution from the ground up, which lets it completely sidestep those old limitations. Right, and this new method, which is based on Murad Sultan Ezouidi's theorem, isn't just a small improvement, it's a whole new playbook. It basically says we don't need to play by the old rules, including that famous Abel's theorem, because it's not even trying to find a solution with radicals to begin with.
So how in the world does it work? Well, this new approach, Ezouidi's theorem, has a method that's actually really elegant and systematic. It's all about looking at the problem from a completely different angle. So instead of trying to find x directly, the theorem breaks the problem down. It uses what's called a recursive process, where each step builds on the result of the one before it to calculate a new set of numbers. These are called symbolic coefficients. Now, think of these coefficients as a kind of hidden blueprint that describes the equation's true underlying structure, but in a much, much simpler way. And this is where it starts to get really interesting. The process kicks off for the very first step, where k equals 1. The theorem runs its calculation, mixing the original numbers from the equation in a really specific way, and the first symbolic coefficient it spits out is 0. Okay, 1 down. Now this whole process is designed to be repeated, with each step digging a little deeper into the equation's structure.
Now we're on to the next step, k equals 2. The calculation gets a bit more involved, pulling in more terms from our monster equation. But you guessed it, after all the symbolic number crunching, the result is 0. Again.
A pattern is definitely emerging here. Is this just a wild coincidence, or is this theorem actually showing us something fundamental about this equation?
So the process just keeps going, for k equals 3, 4, 5, all the way up to 8. And every single time, it doesn't matter how complicated the steps in the middle look, the final symbolic coefficient that the theorem calculates is 0. Every single time.
Okay, so what does this all mean? We've just systematically uncovered the equation's hidden blueprint, and it seems to be made of nothing but zeros. And this, right here, is the key that unlocks the entire puzzle.
So these s values you see here, these are those symbolic coefficients we just found. The theorem lets us rebuild the polynomial using these new, simplified values instead of the original ones. We found 8 of them, and yep, they are all 0. Let's just remind ourselves of where we started. Here it is again, that monster equation. All those big numbers, all those pluses and minuses, just a mess. Now, watch what happens when we swap in that hidden blueprint we just discovered. That minus 16, it becomes a 0. The plus 112, also a 0. The minus 448, 0. All of them, all the way down the line, are replaced by 0. And this is what's left. That entire terrifying equation just collapses into this. X to the 8th equals 0. It's the exact same equation, just seen through a new structural lens. The impossibly complex has become unbelievably simple. And the answer is suddenly obvious, right? X has to be 0.
The theorem didn't just solve the problem, it completely transformed it.
So this is more than just a clever trick for one equation. A result like this suggests a fundamentally different way of thinking about the very structure of these kinds of problems. And this table really clarifies that shift in perspectives. You know, where classical algebra often depends on radicals, those square roots and cube roots we talked about, Ezouidi's theorem doesn't touch them. It gives us a really solid framework for cases with multiple repeating roots, which used to be seen as tricky or marginal, by focusing on their hidden structure instead. The potential power of this theorem really comes down to a few things. Its universality. It's designed to work on polynomials of any degree. Its robustness. It handles those tricky repeated roots that can trip up other methods. Its independence from all those classical constraints. And, of course, its real beauty is in its simplicity. It finds the simple core hidden inside all that complexity. By basically operating outside the traditional stadium, it opens up a whole new pathway for solving problems that were once completely walled off by these very long-standing mathematical arguments. Which, of course, leaves us with a pretty fascinating question. We just watched a method take a supposedly unsolvable problem and boil it down to something stunningly simple. So if this approach holds up to more and more testing, could a new way of seeing these mathematical structures actually begin to rewrite some of the foundational rules of algebra we've relied on for centuries? That's a powerful thought to end on.